Morning, everyone. We're just
Good morning.
about ready to start, so. Okay. How's everyone doing this morning?
Good. How are you?
I'm okay, thank you.
Good.
All right. Okay, well, we'll get started, everyone. Welcome back. I hope you had a nice Labor Day weekend. It was pretty nice weather, except for maybe a little bit on Sunday was kind of ugly for us, but I hope you had a good time and that your families are doing well. So remember, you can always reach out to me privately through email if you're having a challenge. Variety of things are still happening in society, particularly with COVID. So if we need to talk, please reach out to me. Okay, well, we're going to get right into chapter 2 this morning. Of course, we have lab this morning as well, and we'll be going over some more content there. So let's get started. Chapter 2. I will share my screen with you. Okay. Okay. All right, folks. So chapter 2 is the chemistry chapter. I will say that if you're brand new to college, in the sense that you haven't been in school in quite a while, that this is a chapter that tends to scare students. But I don't want you to be scared. Like most things that are difficult, if you break it down piece by piece, do a little bit every day, it does become manageable, okay? So we're just going to start that journey. We have 3 lectures scheduled on the syllabus to cover chapter 2. All right, let's start with some definitions. Okay, the first definition is chemistry, okay? Chemistry. Okay, what the heck is chemistry? Okay, so I have a chat message in the chat window that I need to respond to. Let me ask this question in the chat window. Can everyone hear me okay? Is my audio coming through okay for you? Okay. All right. So I have one person online who says they cannot hear me. I don't know your name because your login information is a telephone number. But I suspect that if you cannot hear me, the problem is on your end. So see if you can tweak some settings on your computer and see if that helps. Okay. So chemistry, what is it? Chemistry is the science of matter. Okay, now we'll define matter in just a moment. In fact, that's what we'll do next. Okay, chemistry is the science of matter. And well, what the heck do I mean by matter? Matter is anything made of atoms. Anything made of atoms. Okay, so in fact, what we will start really with chapter 2 on is talking about, well, what are atoms? What are they made of? So let's talk about atomic structure. And for atomic structure, this is not a chemistry class, but there is a little bit of information on page 31 of your textbook, page 31, talking about the structure of atoms. Okay. You will not be a chemistry expert by taking a biology course and getting one chapter in your textbook on it, okay? But we can introduce you to some basic principles, okay? So let's talk about atoms, okay? We talked about the relative size of matter in your body in chapter 1, and it all started with that carbon atom. You remember that in the University of Utah Genetics Learning Center website, Showed you a carbon atom about 320 picometers wide. That's an example of an atom. I like to think of atoms as the building blocks of matter. I might even say they are the Lego bricks of matter, right? Maybe you have Lego bricks at the home that your children play with, or maybe you still play with them. That's okay. You link them together in different arrangements, different patterns, different organization to build larger structures like robots, doll houses, whatever it might be. Well, when you link atoms together, you build molecules, right? Atoms are the building blocks of matter. They are the Lego bricks of matter, okay? If we talk about atomic structure, what are we going to find? Okay, well, we're going to find that an atom is made of basically 3 subatomic particles. Okay, we will find protons, neutrons, and electrons. You see them defined in figure 2.1 at the bottom right corner of page 31. Okay, this probably is digging out some cobwebs from other things you learned a long time ago, right? Protons are subatomic particles. Okay, they are found in the nucleus of the atom. Okay, so you see what the nucleus is defined as, kind of looking at figure 2.1 there. The nucleus is the area of the atom where you find the protons and the neutrons. So protons are found in the nucleus, and they are particles that have a positive charge. Okay. Of course, if this were a physics class, you might ask yourself, well, what is a proton made of, right? Because it seems like we can always break something down into smaller and smaller individual components. And that's largely true, right? But we won't go any further than protons in the conversation of our course, right? If you're really interested, you can read up about that. I mean, protons are made of things known as quarks and other exotic particles that physicists care about. So protons are positively charged particles. They're found in the nucleus. Neutrons are also found in the nucleus. And they are particles that have no charge. They are neutral, okay? All right. Electrons are found outside the nucleus, and they actually orbit around the nucleus, kind of like planet Earth orbits around the sun, right? That kind of thing. Electrons are found outside the nucleus. And electrons have a negative charge. They are negatively charged particles. Okay, so we know that atoms make up everything that we can touch, right? I mean, the computer desk that your computer is on right now is made of material made of atoms, right? Your book, the books in your room, the wall that you're looking at, even the glass window you're looking through is made of atoms, right? But also other things are made of atoms that don't have quite a solid appearance to them, right? Think about liquid water that you bring out of your faucet, right? That's made of atoms. Think about the air that you just inhaled into your lungs, right? That air is made of molecules that are in a gas state, but those molecules are also made of atoms. Think about the oxygen that you just inhaled into your lungs. That's made of 2 atoms of oxygen linked by a covalent bond. So it's diatomic oxygen. Okay, that is made of atoms. Everything that we think of in our reality, in our daily lives that we interact with and touch is made of atoms. Okay, now from our conversation last time, because I asked you to give me some examples of atoms. Now, we had carbon up there. I think someone told me about hydrogen, oxygen, maybe nitrogen. all the atoms on the periodic table of elements, that thing that you might have run away from in chemistry class in high school, these are different kinds of atoms, Okay, so there are many different kinds of atoms. So I'm going to start my next statement with a question. What characteristic of an atom defines the atom's identity? Hey, do you know the answer to that? If you know the answer to that, please speak up. Please type something into the chat window. What characteristic, and that should not be plural, what characteristic of an atom defines the atom's identity? Okay, if you had a carbon atom in your left hand and a nitrogen atom in your right hand, how would you tell them apart? How would you know one's a carbon atom and one's a nitrogen atom? How would that happen? Okay, so we're getting some nice answers in the chat window, and I would encourage you to monitor that. Okay, so Lauren and Amy, you are absolutely correct. It comes back to a characteristic known as the atomic number. Okay. All right, so let's define what atomic number is. Atomic number is the number of protons present in the nucleus of an atom. Okay, so what I'm telling you is the atomic number is that characteristic of an atom which conveys or gives the atom a unique identity. It's how we can tell atoms apart. Okay. Okay. When when you're at the zoo, think about the last time you may have taken a visit to the zoo. When you're at the zoo, you can tell the animals apart, right? You can tell a giraffe is different from an elephant, is different from a lion, is different from a pink flamingo. You can tell the animals apart simply by looking at them, because they look different colors, different shapes, different sizes. These are characteristics of the animals that allow us to tell the animals apart. Different kinds of animals look different. Well, with atoms, it's harder to do that because they're so tiny that we can't see them with the naked eye, right? So what chemists came up a long time ago is measuring a property, a characteristic, which is the number of protons in the nucleus, which is unique for each different kind of atom. Okay. Hold on a second here. All right. So please turn, if you have your book available, please turn to page 32. Please turn to page 32. And let me ask a couple questions here in the chat window. What is the atomic number of nitrogen? Okay, does everybody see that? Is everybody able to draw that out of their textbook? Okay, Lauren and Christina, Amy, they've all done it. Okay, you can see that is in fact 7, right? So we know that every nitrogen atom has 7 protons in its nucleus. All right, one more question. What is the atomic number of chlorine? Okay, you all facts, you got it. Good job. All right, it's 17. My point here is that by looking at figure 2.2, you have a description of 8 different types of atoms that are found on the periodic table of elements. These are atoms that are of particular relevance to living organisms. And you notice as you scan across those 8 atoms, you notice that none of them have the same atomic number. None of them have the same atomic number. In other words, the atomic number is unique for each different type of atom, each different kind of atom, each chemical element. Okay? So atomic number is a very important characteristic to be aware of. All right. Any questions so far? By linking the different kinds of atoms together, right, we will build the molecules like H2O, 2 atoms of hydrogen, 1 atom of oxygen. All right. So there are some other characteristics of atoms that are kind of interesting and that we would want you to be a little bit familiar with. One of those is, in fact, mass number. Okay. Mass number is the number of protons plus neutrons in the nucleus of a single individual atom. Okay, the number of protons plus neutrons in the nucleus of an individual atom. Okay, of an individual atom. Now, let's do a couple questions here in the chat window. Okay. So, what is the mass number of carbon? What is the mass number of carbon? Okay, all right, so I'm seeing some answers there, right? And some of you did put down the wrong answer. Okay, it is 12 or 13. It is not 12.01, right? Be very careful that you're not too rapid in looking at your information there. It's 12 or 13, okay? So here's a question that comes up. Well, let me put this down. Notice how your textbook reports that the mass number of carbon is 12 or 13. Okay, folks, question in the chat window, but I'd be really happy if somebody could unmute and try to respond to me. How can a mass number have multiple alternative values? I'm going to type that question also into your notes. Okay. What do you think, folks? How can a mass number have different values? How can a mass number have different values? Have you been reading anything in your textbook that leads you to think about this?
Is it because of the different neutrons that are in them?
Okay, Christian, please stay with me. Thanks for unmuting and speaking up. Christian, you said, is it because of the, I think I heard you right. Is it, you said, is it because of the different neutrons? Is that what you said, Christian?
Yes.
Okay. That you are definitely getting to the answer here. So, Christian, does that mean that we can have 2 carbon atoms that are both carbon atoms, but in some way be subtly different? Is that what you're telling me?
Yes.
Okay. So if I have 2 carbon atoms that are both carbon atoms, but they're subtly different, what kind of vocab word am I fishing for? These carbon atoms are blank of each other.
Aren't they called isotopes?
Okay, thank you, Sierra. You're absolutely right. That's what I'm fishing for. Rebecca, I see it in the chat window. Good job, everybody. You're working as a team to pull this together. How can a mass number have multiple alternative values? Okay, so think of it this way. An individual atom only has a single mass number, but two atoms that are both the same can be subtly different. Okay, we are referring to isotopes. Okay, so question, what are isotopes? Okay, gang, isotopes, as you've been reading in your own textbook, right? Isotopes are as a boldface word, page 32. You have isotopes on the left-hand column. On the right-hand column, you have radioactive isotopes. Isotopes are atoms that have the same atomic number, but different numbers of neutrons in their nucleus. Isotopes refer to atoms that have the same atomic number, but differing numbers of neutrons in their nucleus. Okay, so what are we saying here? Look at figure 2.2. It tells you that the mass number of carbon is 12 or 13. What does that mean? That means in the universe, in Mother Nature, there are some carbon atoms. Well, before I give away the punchline here, I'm going to ask you a few questions. Okay. All right. So let's see here. I like to get you guys involved, talking and thinking about things, particularly at 8 a.m. It gets pretty tough to do some of this. So hold on a second. Okay. All right. So Phaedra, please unmute your microphone and say hi to us.
Hello.
Good morning, Phaedra.
Hi.
So Phaedra, I'm going to ask you a question. Do you have your textbook up on your computer screen?
No, I'm actually having a really tough time because I've been having connection issues for like the past 20 minutes. So I finally just got in on my phone just so I didn't miss what you were saying.
Okay, Phaedra, I appreciate you telling me that. And you know what? Just for now, I'm going to move to a different student because I really need someone that's looking at their book to answer my question. So let me know if you need some help on that later on, okay?
Yeah, I'll probably be emailing you to see if there's a recorded.
Okay.
Thank you.
All right. Let's continue here. Let's try Amanda Amadeo. Amanda, please unmute today.
Hi, good morning.
Morning, Amanda. Amanda, do you have your textbook up on your computer?
I do.
Okay. So Amanda, on page 32, so let's do this. Number 5 here, questions about carbon atoms. So Amanda, here's my first question to you. Amanda, how many protons are in the nucleus of a carbon atom?
Six protons?
You're absolutely right. Good job, right? That's the atomic number. That's what you reported, right? 6. That's the atomic number. So stay with me, Amanda. So Amanda, if a carbon atom has a mass number of 12, how many neutrons does it have? Once again, Amanda, if a carbon atom has a mass number of 12, how many neutrons does it have?
6 neutrons.
Okay, I believe you said 6. Can you just be over the top and explain to everybody how you arrived at the answer of 6?
Because since the mass number is 12, don't you divide it by the amount of neutrons?
Okay. Amanda, you did give me the correct number, but I'm not comfortable with your explanation. You wouldn't divide anything, would you? So in other words, if the mass number is 12, and we already know the number of protons is 6, it would be 12 minus 6, which equals 6. 12 minus 6 equals 6, so there are 6 neutrons present. 12 minus 6 equals 6 neutrons. So Amanda, let's do this again. If a carbon atom has a mass number of 13, Amanda, how many neutrons does it have?
Seven.
Okay, and you arrived at that number by doing what?
You subtract the number of neutrons.
You subtract the number of neutrons. Well, you don't know the number of neutrons, so you can't subtract the
Or sorry,
number.
the number of protons from the mass number.
Okay, good job, Amanda. Good job. So, folks, thank you, Amanda. You did fine, but please understand that there will be times where not only do you have to give me a correct answer, but you actually have to give me a correct explanation, right? So I will pick on your explanations on exams and say, well, okay, your answer was right, but the logic of your reasoning does not justify your answer. I'm going to ask you those sorts of things on exams, okay? So, excuse me, 13 minus 6 equals 7, right? 7 neutrons. Okay, good job, everybody. All right, any questions so far? Okay, so in your textbook, and I'll just open this up to anyone that wants to answer. Okay, in your textbook, the mass number of carbon, that is 12, is highlighted in bold face font. Why? Why is the 12 highlighted in bold face font? Why is that? What is the, does that tell us any information? The fact that that is in boldface font. The number 12 for the mass number of carbon is boldface, but the number 13 is in normal unhighlighted face font. What does that tell you? Okay, so Christina, Lauren, I see some answers there. Okay, right. What the book is telling you is that in terms of what we know on planet Earth, 12 is the most common form of carbon atoms that we encounter. In other words, of all the carbon atoms making up all the molecules inside your body, 99.99999% of them are in fact carbon-12 atoms, right? The bold is telling you the most common or prevalent version or form of the atom. Most common, most frequently found version of the atom that is present. Okay. All right, gang. So, isotopes, if you need an analogy, here's the analogy that I sometimes use. If you need an analogy, okay, we're back up here to the definition of isotopes. What are isotopes? These refer to atoms that have the same atomic number, but differing numbers of neutrons in the nucleus. Isotopes are like the word, here's my analogy. Isotopes are like the word ice cream, right? Ice cream is ice cream is ice cream. Yet we can have different flavors of ice cream, right? We can have chocolate ice cream, strawberry ice cream, vanilla, peanut butter, whatever version of ice cream you like, right? Okay. isotopes are like ice cream, okay? All ice cream is ice cream, yet we have different flavors. Okay, all right. Okay, gang, any questions so far? What I'm going to do is talk to you about one more related vocab phrase, and then I'm going to come back to isotopes and talk to you about their medical importance, okay?
Dr.
All right.
Allen, I have one question, sorry.
Okay. Yeah,
So the only way that carbon would have a mass number of 13 is if an isotope was present? Or are isotopes always present? Sorry.
okay, very good question. So hold on a second. Who is talking there?
Amy.
Hi, Amy. Amy, let me help you answer your own question. Amy, do you have your textbook up on your computer?
Yes, I do.
Okay, so Amy, please tell me what the mass number of sodium is.
23.
23. So at least according to your textbook, Amy, is there any other version of sodium according to your textbook?
No.
That's the answer to your question. Not all atoms have isotopes.
Okay.
Not all atoms have isotopes, but some of them do.
Okay.
Okay,
That does answer my question. Thank you very much.
you're welcome. Any other questions? Now, of course, you could ask yourself, well, why do isotopes exist? And that's a good question, but it's almost the kind of question in the same variety of, well, why did God create it this way? Because we just don't know. There are certain things that exist in the universe. We observe them, we measure them, we know they're there. We don't know why they're there. Okay, so it's a reasonable question that's not really answerable. Okay. So in relationship, so far, look what we've accomplished, right? We've defined atoms, we've defined atomic number, we've defined mass number, and we've answered some questions about these ideas. There's one more phrase, vocab phrase that I want to put into your notes, and that is atomic mass. Okay, atomic mass. Okay, atomic mass, for those that are old enough or might have been around the block a little bit longer, as your own book on page 33 shows you there, when you see the phrase atomic mass in bold in the left column, it has in parentheses also called the atomic weight. So when I was coming up through college, I was taught this concept as the phrase atomic weight. Atomic weight has been deprecated over the years because it's not quite technically correct. And so a more modern and more precise terminology for the concept we're about to share is atomic mass. Atomic mass is the average number of protons plus neutrons in a group of atoms. Okay, so this is extremely important to contrast this. So remember, mass number is the number of protons plus neutrons in the nucleus of a single atom. Okay, so mass number is referring to the number of protons plus neutrons in the nucleus of one atom, but atomic mass is talking about a group of atoms. And that's why when we have a group of atoms, we can talk about an average, right? I mean, your family might have 4 people in it, or your family might have 5 people in it, but the average number of persons in a family might be 4.5, right? So that's why when you look at atomic mass, the values for atomic masses are not necessarily integers, they're not necessarily whole numbers. They can have fractional pieces. For example, okay, notice in your textbook, page 32, that the atomic mass of chlorine is 35.45, right? In other words, notice that it has this fractional part, 35.45. How can you have a fractional part of an atom? You cannot have a fractional part of an atom, but you can have fractional parts which represent averages of groups of atoms. Averages of groups of atoms. Okay. All right. Folks, are you okay? Do you have any questions right now? Okay. All right. Please let me know. All right. So I mentioned to you that I wanted to come back and talk to you a little bit about the clinical relevance of the term isotope. Okay. Okay. Let's talk about this. Medical importance of isotopes. And I don't want to get into a heavy physics conversation with you today, but I want you to see that there is practical clinical relevance to the idea of isotopes. Okay. And so I want to outline some ideas for you here. Okay. We already know from the information we've covered this morning that the most common form of carbon atoms present in your body are carbon-12 atoms, right? That's the mass number that's highlighted in bold phase, okay? The most common type of carbon atom in your body is carbon-12. That's the mass number, okay? It's not the atomic mass, it's the mass number, okay? So this comes up when this topic of the importance of isotopes comes up when we're talking about disease processes. So a question becomes this: if you have a tumor or cancer, okay, technically there is a difference between those two things, but right now we won't worry about that. If you have a tumor or cancer, how can you locate that tumor in the body? How can you locate that tumor in the body? Okay, well, here's the deal. Okay, all the cells, including the tumor/cancer cells, will be made of carbon-12 atoms in your body. And so what medical science has done and what medical physicists, okay, this is a physics thing. What medical No, when you go, when you go get a fancy diagnostic test at the hospital, let me ask you this. If I could type properly, that would help. Have you ever had an MRI done? Well, some of you have, maybe some of you haven't, and that's good. The point is this: these big fancy machines and gadgetry that we use to diagnose and sometimes treat things, many times they've been created and built by physicists and engineers, not by chemists, not by biologists. Okay, so when we need to look into the window of the human body using X-rays or other alternative technologies, that gets into the realm of physics, okay? So at any rate, you'll get specialized training on those things later if you're involved with the use of these technologies. But I come back to my talking point question. If you have a tumor or cancer, how can you locate that tumor in the body? Well, let's first start off with the idea that all the cells in our body are going to be made of molecules that are made of carbon-12 atoms, okay? So before I continue and answer that question, we have to ask ourselves, what characteristics define a tumor or cancerous cell from healthy cells in the body? Okay, anybody want to contribute to that? What characteristics define a tumor or cancer cell from healthy cells in the body?
Unusual growth.
Unusual growth. Okay, so I'm sorry. Sometimes I can't tell who's talking. Who answered that?
It was Jay.
Jay? Okay. Jay, thank you for answering. Jay, let me just ask you, Jay, when you say unusual growth, for a cell to grow, does that mean it's using a lot of resources?
Yes.
Okay, so Jay, if a cell is using a lot of resources, would it make sense that the cell probably has an accelerated metabolism?
Yes.
Okay, thank you. That's what I was fishing for. So, there's numerous characteristics we could say here that define a cancer cell, but probably the thing that's most relevant for our conversation right now is an elevated or accelerated metabolism. Okay, what I'm saying to you is, and I'm just speaking in general rough terms, I'm not being super precise from a physics standpoint, that, let's say that you eat a cheeseburger. Well, maybe you think about the amount of energy in that cheeseburger from a biophysics perspective. You might say that, you know about calories and how calories are units of energy, that we can measure the caloric content of a food like a hamburger or an apple or something like this. Okay. Tumor tissue, cancer tissue, because of its desire to grow and reproduce, it will have an accelerated metabolism. To feed that accelerated metabolism, it needs to kind of be the bully on the playground and grab most of the energy out of the food you eat. So in a very rough analogy, what I'm saying is you eat a cheeseburger and maybe 70, 80% of the energy content of that cheeseburger goes into the tumor rather than the normal surrounding healthy tissue of your body. Most of the energy, most of the molecules in the hamburger are going to be taken up, scavenged, metabolized, used by the diseased tissue. Okay. So an elevated or accelerated metabolism. Okay. Meaning the disease tissue will dominate where molecules from food are used. Okay. So if we are okay, or at least comfortable with the idea that a tumor or cancerous cell is going to be very hungry and grab material from the food that we eat, if we had a way of spiking the food we eat with something that's not normally found in the body, let me say it again, if we had a way of spiking or creating food that is made of materials that are not normally found in the body, and then we had the right technology to locate where this different kind of material is, it should show up in the body. It should show up where the cancer tissue is. And in fact, that is what is done. Okay. During diagnostic testing, cancer is often detected by having a patient eat, meaning consume, a material. It could be a food, or it could be kind of like a really gross milkshake kind of thing, okay, that has molecules made of different types of carbon atoms, like carbon 13, right? So we know that carbon 13 is an isotope of carbon 12, right? Carbon 13 is an isotope of carbon 12. All right, we've defined that. We've answered some questions. We know that carbon 12 is what is normally found in our cells, but carbon 13 is not. Carbon 13 is not normally found there. So if we feed a patient food, quote unquote, food that is spiked with carbon 13 atoms, And we know that cancer is going to take up most of the material from the food we eat because it has an aggressive metabolism. Doesn't that make sense that most of the carbon-13 should end up in the cancer cells? Okay, question in the chat window, folks. Are you with me? Am I making sense here? Okay, let me say it one more time. If we feed a cancer patient or someone suspected of having cancer food that is spiked with a version of carbon that is not normally found in the body, such as carbon-13, then that carbon-13 will be preferentially taken up by the diseased tissue because the diseased tissue takes the majority of molecules to support its aggressive growth. So we feed folks food with carbon-13. If there is cancer there, the carbon-13 cancer takes up the carbon-13, soaks it up like a sponge. And then if we have the right equipment in the lab to detect the presence of carbon-13, that will highlight the location in the body where the tumor or cancer is actually present. Okay. So, because cancer will preferentially consume material put into the body if we place carbon-13 in the body, we can locate the cancer or tumor. Okay. So, in a nutshell, without using a lot of fancy physics or getting into a biophysics kind of conversation, I simply want you to appreciate that this idea of having alternative forms of atoms, isotopes, can actually be extremely useful when you want to locate diseased tissue in the body. And the most common topic for this would be cancer. Okay. Do you have thoughts or questions?
Don't they use radioactive isotopes for treatment? Isn't that what chemotherapy is?
Yes. Radioactive isotopes can be used for treatment. Radioactive isotopes can also be used for the diagnostic imaging that I'm thinking about here. Not all atoms are radioactive. If an atom is radioactive, that means it's unstable, so it will eject certain materials from its nucleus in an attempt to become more stable. And so in some cases, you can feed a cancer or a tumor radioisotopic material, and as that radioisotope ejects material from its nucleus, it will damage the cells that material is in, so that can be a treatment for cancer. You're absolutely right. Of course, we have toxic side effects we have to worry about. There's a lot of things like that, but you are at first principle correct that can be done. Other questions? Okay, gang. All right. So I'm going to let that rest for right now. We've been talking about a lot of definitions here today. What I'm going to do next is shift gears to the topic of chemical bonds. All right, so we've been talking about atoms. We've been talking about their characteristics and features. We've mentioned isotopes, showed you a little bit about their clinical relevance in the hospital. Now let's talk about chemical bonds. So chemical bonds is a topic that starts on pages 34, 35, 36, 37. Okay, big important topic for us here. Okay, and okay, so where to start this topic? Okay, there's lots of things. There are more types of chemical bonds that exist than are defined in your textbook. There are more types of chemical bonds that exist than are in your textbook. But we're going to stay with the three major varieties that are defined in your textbook because that will be of most relevance for your education and future career. Okay, so there are three major types of chemical bonds. Okay. They are ionic, covalent, and hydrogen. Okay, now before we talk about each individual type of bond, I want to give you a framework for thinking about the bonds, kind of like an overview here, okay? When you read books, it's very easy for a new student to think, okay, an ionic bond is this thing, a covalent bond is this different thing, and a hydrogen bond is yet another different thing. These are different things because they're different types of bonds. But I want to flip that on its head and get you to think about the fact that ionic bonds, covalent bonds, and hydrogen bonds are really quite a bit alike. They're not so different, okay? While you may think from reading your textbook that ionic, covalent, and hydrogen bonds are really different beasts, quote unquote, okay? In reality, they are very similar. Okay, in reality, they are very similar. So, bear with me a moment. Occasionally, I will attempt to draw something on the computer screen because drawing might give you a better idea of what I'm trying to convey to you. Okay, so for example here. For example, think about a triangle. Think about a triangle. Okay, so let's see if I can do this. All right, so here is a triangle. Poorly drawn, but nonetheless a triangle. All right, so here's a triangle. What I want you to think about is this, okay? That triangle has three sides, doesn't it? Whether I point to the left side, the right side, or the bottom side, okay, here's a question coming in the chat window. If I point to the left, right, or bottom edges of a triangle, am I still pointing to the same triangle? Okay, I hope you can agree that yes, I am. I'm pointing to the same triangle, okay? And so that's how chemical bonds are. Chemical bonds are like different edges of a triangle. Chemical bonds are like different edges of a triangle. And so what I'll do is just put this in a different color here. Okay, so one edge might be the ionic edge. The other edge might in fact be the covalent edge. And the bottom edge might be the hydrogen bond edge. Okay. So the three different types of chemical bonds, even though they are different types, they're still part of the same triangle. They share a lot of similarities. And, you know, so, okay, so I'm going to stop drawing now and go back to just typing in text here. At least I hope I'm going to do that. Okay. Okay, come on, work with me here. Okay. What is the commonality between the different types of chemical bonds? Here's the commonality. Okay, all three types of chemical bonds refer to an attraction between oppositely charged particles. All three types of chemical bonds refer to an attraction between oppositely charged particles. Okay, so what are these oppositely charged particles? Well, you already know they are protons and electrons. Protons and electrons. Protons have a positive charge, electrons have a negative charge. Okay. All three types of chemical bonds refer to an attraction between oppositely charged particles. So the triangle itself in the center would be this attraction between oppositely charged particles. Well, what allows us to define one edge of a triangle as separate from a different edge? Okay, what allows humanity to define different types of bonds, here it is the magnitude of the attraction. The magnitude of the attraction is what allows us to define a chemical bond, hydrogen bond, covalent bond. Okay, it's like, it's kind of similar to, going to the shopping mall and just sitting and watching people go by, right? I kind of like to do that because, people are odd, right? People are strange. So am I. I'm odd. I'm strange. Sometimes it's fun to just watch people and say, wow, that's an interesting person, right? Look at that hairdo, whatever. Okay. But the point of it is this: you might be looking at three different people. And one person you say, well, that person's kind of pudgy. And you might look at a different person and say, well, that person's overweight. And you might look at a third person and say, well, that person's obese. Okay, so here's a question in the chat window. What is the common idea shared between terms like pudgy, overweight, and obese? Pudgy, overweight, and obese. Okay, so Phaedra, you mentioned weight. Okay, can we take that a little bit further? Don't these terms suggest something about how much excessive body weight a person is carrying? How much excessive body weight a person is carrying? I mean, I think if you see somebody that's carrying just a little bit too much body weight, you might say pudgy. Whereas if you see someone that is clearly at an unhealthy body size, and this is not about body shaming, that's not why I'm picking this. If someone's carrying an unhealthy amount of body weight, you would say, well, that person's obese, right? Okay, right, so body weight index, body mass index, okay? The idea here is that these different adjectives are describing different amounts of carrying too much body weight. Well, in a similar vein, these bonds are describing how intense the attraction is between the protons and electrons. So these are all the same idea, just in different magnitudes, different intensities, different severity. Okay, so thoughts or questions, folks? Okay, well, let's define these things then. Let's see. So we're talking, all right, since we're talking about magnitude of attraction, let's make a little table here. Let's make a little table here. Okay, so I'm going to insert a table into your notes. All right, so let's do this. Type of bond, strength of attraction, bond length. Okay, type of bond, strength of attraction, and bond length. Okay, so we're not going to put numbers down, we're just going to put descriptive language down. Okay, but we have ionic bonds, we have covalent bonds, and we have hydrogen bonds, and these are not necessarily listed in any specific order, they're just listed down. Okay, so in the chat window, here we go, in the chat window, here we go. What type of bond has the strongest attraction between oppositely charged particles? Anybody? Okay, thanks for everybody that's participating. I really appreciate that. And again, don't be shy. Don't be afraid to be wrong. We just want to have a conversation. So we do have a difference of opinion between Lauren and Jay, and between Lauren and Jay. So let me just clarify here. And you might not have an opinion because you just don't know what to think about this. So the bond with the strongest type of attraction is covalent. Okay. So covalent bonds have the strongest attraction. Hydrogen bonds have the weakest attraction. And ionic bonds have a middle attraction. This is, we could put some kind of number on this with a unit, but for right now, I don't think that's necessary. So strongest bonds are covalent bonds, next ionic, next hydrogen. So let me ask you this in the chat window. What type of bond has the longest bond length? What type of bond has the longest bond length? When I say bond length, I'm talking about the length between the center of each atom that's at the end of the bond. Okay. All right. So Sierra and Christian are saying hydrogen bond. Do the rest of you agree with them? Okay. All right. Thanks, Danielle. Okay. So there is a difference of opinion here. And it turns out that in this case, the hydrogen bond does have the longest bond length. Okay. Hydrogen bond has the longest bond length. Covalent bond has the shortest bond length. And ionic bond, once again, finds itself in the middle. Okay. So if this isn't making too much sense to you, think about this. All right. If a hydrogen bond is the weakest sort of attraction between two atoms, if it's the weakest attraction, then it has the least ability to draw atoms towards itself, which means it should have the longest bond. In a similar analogy with human relationships, think about if you've ever had a dating relationship with someone. Think about the dating relationship when someone lives in your same town versus the dating relationship when you've tried to have a long distance relation with somebody living in a different state, right? Isn't it a lot harder to maintain a relationship when the person's not physically close to you in the same town, right? A relationship with somebody across the country is simply a lot harder to maintain. So it's kind of the weakest attraction because you have the greatest distance between you, okay? So that's how you should conceive of these sorts of characteristics of bonds. Now, in a proper chemistry and maybe physics class, you would go into numbers on this. I don't want to do that right now. I'll leave that to your chemistry teachers when you take chemistry courses in the future. But we do need to start talking about what these bonds really are and put a definition down for each type. We know that they are different types, but they really are very much similar to each other, very much similar to each other. Do you have questions right now? Okay. Let's talk about bond definitions. Okay, we'll start with an ionic bond. Okay, an ionic bond is an attraction created between atoms when one atom donates or transfers one or more electrons to a neighboring atom. Okay, an attraction created between atoms when one atom donates or transfers, if you prefer that word, one or more electrons to a neighboring atom. Okay. All right. So there's many ways we could talk about this, but it's pretty common for textbooks to talk about sodium chloride. So let's do that. Okay, we're going to talk about sodium chloride, and I'm going to go back to drawing a little bit because it's just easier for me to communicate to you in this regard. Okay, so figure 2.4, page 34 is giving you an example of a substance which is an ionic substance, sodium chloride, and it tries to describe to you the nature of an ionic bond between the sodium and chlorine atoms. Okay, so please interrupt me with questions if you have them. All right, so let's think, for example, about sodium chloride. Okay, sodium chloride right? This is table salt. And undoubtedly, if you ate anything this morning, even cereal, it had some measure of salt in it. Sodium chloride is an ionic compound. So what do I mean by that? It is a molecule made of two different things, a sodium atom and a chlorine atom. That's what it means, okay? A molecule with two different atoms. Okay, that word compound means something that's made of two different kinds of things, at least two different kinds of things. All right. Now, sodium and chlorine don't start out together. They start out separate as individual sodium atoms and individual chlorine atoms. Okay, so what I'm going to try to get you to understand in the next 5 minutes is why sodium and chlorine are attracted to each other. So we start out with a sodium atom. We start out with a chlorine atom, and I'm intentionally drawing them apart. I'm trying to convey a sense of distance or space between them. Okay. Now, all right. So let's see here. Okay, is Veronica Mendez. Veronica, could you say hi to us, please? Okay, Veronica, can you hear me? Can you unmute your microphone and say hi? All right, maybe Veronica is having some technical problems, so I'll move on. So let me ask Nick this morning. Nick, could you say hi to us?
Morning.
Morning, Nick. So Nick, do you have your textbook available on your computer?
On my computer, yeah, I just need to pull it up real quick.
Okay, yeah, please do so. I want to ask you some questions. Let me know when you have your textbook up.
Do you want the lab textbook or the lecture textbook?
the lecture textbook.
Okay.
Okay, Nick. So Nick, please turn to page 32 and have a look at figure 2.2. You okay, Nick?
Yeah, I'm just getting there right now.
Okay. So folks, remember, please, when you get ready for class every morning, have your textbook already preloaded on your computer because you never know when I might be asking you something, okay? So please bring that textbook up at all times. Okay, Nick, are you there?
Yeah.
Okay, so Nick, on page 32, can you please tell me how many protons are in the nucleus of a sodium atom?
Uh, nine.
Okay, that is not correct. You want to try again? So for the sodium atom, how many protons are in the nucleus?
I don't know.
Okay, Nick, thank you for trying. Remember, and this is not specific to Nick, but it's for everybody's benefit, right? We need to be in the game with our thinking during lecture. We need to be in the game. So we'll come back to you another time, Nick. Let's try this. Okay. Christina Pace. Christina, please say hi to us.
Hi.
Hi, Christina. Christina, do you have your book?
Yes.
Okay. Christina, could you answer that? How many protons are in the nucleus of a sodium atom?
11.
Okay, that's absolutely right, because that's the atomic number, right? So I'm going to draw here 11 protons in red, 11 positive particles, right? The positive is the proton, right? 11 protons here by the sodium atom. Okay, so Christina, since there are 11 protons in the nucleus of the sodium atom, how many electrons should be present outside the nucleus?
11.
How do you know that?
Because it's the mass number is 23. So well, it would be 11 plus 11, right?
11 plus 11 is 22, right?
Yeah.
So that's not 23. So Christina, I'm picking on you, but let me ask you this. Does your explanation seem to be logically correct?
No.
Okay, thank you for your honesty and your courage to say so. You gave me the right answer, Christina, but you gave me the wrong explanation. And again, this is for everybody's benefit. On exams, I will ask you for the answer and the explanation. So we're getting short on time, but let me say it this way. Christina, the reason there are 11 electrons is because of something that you may not even appreciate yet, but I'm going to tell it to everybody now. All the atoms on the periodic table of elements, all the atoms listed in figure 2.2 are defined as electrically neutral. Okay, let me write this up here. Atoms are defined as electrically neutral. So Christina, if I have a sodium atom that's electrically neutral, and I'm telling you it's got 11 positively charged particles, how many negatively charged particles does it need to counterbalance the positive particles?
11.
You got it. That's how you reason with this, okay? So 11 positive protons in sodium, 11 electrons. Okay, let's continue. And I know I'm just about out of time, but let's finish a little bit of logic here. Chlorine atoms, page 32. Nick, page 32. Nick, how many protons are in the nucleus of a chlorine atom?
17.
You got it. So Nick, how many electrons does it have?
17.
You bet, because it's got to be electrically neutral. Okay, so that's how you figure out protons and electrons. Okay, so folks, I am basically out of time here, so I should respect our window here. We will pick it up here next time with class. We do have lab this morning, and so I'm going to pause the recording.